This conference will now be recorded.
And the invite to come and speak, even though I generally have to be badgered to do these sorts of things. But anyway, so yes, hello everyone. My name's Mark Burstow. I work for Network Rail within the technical authority. I'm Principal Vehicle Track Dynamics Engineer, which is a bit of a long-winded title, but it just means that I'm a specialist in vehicle track interaction. Today we're going to be talking about derailment investigation, which should form a small part of my job, but sometimes it feels like it forms a much larger part of it. Yeah, so as part of my job, I get involved in a wide range of sort of vehicle track interaction issues, of which derailment investigation is one. But you know, historically, a lot of sort of rolling contact fatigue, wheel and rail wear sorts of issues as well. But today we're talking about derailment investigation. So what I want to talk about is first as a bit of an introduction as to how derailment investigation has developed over the last few years, and then basically take you through the process of an investigation with a bit of a sidetrack along the way to talk about the mechanisms of derailment, to give you an idea of the sort of things or the mechanisms by which a derailment can happen, and therefore the sorts of evidence and the indications we're looking for that. We'll then go through sort of all the things, the sorts of things that we can look for on site, and then how we can actually use those to piece together how a derailment occurred and look at the contributory factors. So let's start at the beginning then. So accidents and derailments have always been investigated ever since the dawn of railways. It's a good thing to do to make the railway safer, to really understand what's happened. And I mean, really, you can look at the rule book and you'll find that every rule that exists in the rule book is as a result of an incident and trying to stop that sort of thing happening again. But derailment investigation really became a bit more of a science in the 1960s. There were a lot of changes on the railway through the 1960s. Introduction of CWR, transition from steam to diesel, and then electric traction. And one of the things that was noticed was a marked increase in the number of derailments, a worrying increase in the number of derailments, particularly of freight trains and with short wheelbase two-axle wagons. The plot on the graph there shows that actually there was just this sudden increase up to about 400 derailments a year up to the late 60s. And the Inspector of Railways at the time, I've listed 4 of the sort of the significant derailments during that time, which were picked out by the Inspector of Railways in their report, saying that really there was not a good explanation as to why these derailments were happening and why there was such an increase in the derailments. So people put it down to the introduction of continuous welded rail and use of new forms of traction, but there wasn't really a solid engineering explanation of why things were getting worse. So welcome the, well, before we talk about how that changed, it's good to see that the developments that took place, and largely because of our understanding and research that was done and improvements to the investigation process, that actually from the late 60s, the number of derailments significantly reduced. And now in the sort of 2020, we're looking at less than 10 derailments a year for the last few years on running lines. I'm excluding derailments in depots and sidings, but derailments on running lines, less than 10 for the last few years. Total derailments, which is a really good position to be in, but it also does bring problems. But back to the 1960s then, and what was actually done to try and stem this increase in the number of derailments. Well, step in the newly formed BR research department with its wonderful base on the at London Road and Derby. And they were basically put in the challenge of researching vehicle dynamics, and part of that was to better understand the mechanisms of derailment and how that can be solved or prevented. And so they really developed a lot of the theoretical understanding of vehicle dynamics, which has then seen, well, it resulted in the development of new trains, the HST and the APT in particular. That really came out from an understanding of vehicle dynamics, wheel-rail interaction, and being able to better utilize the wheel-rail interface to its limits. But in the investigation of some of these early derailments, they really identified that some of these wagons were actually becoming dynamically unstable and started hunting with an unstable oscillation of the wheel sets at speeds as low as 20 miles an hour in some case, which wasn't particularly good for trying to run freight trains. Doesn't do much for your business case when you can only run a train at 20 miles an hour. And so this research really sparked a better understanding of the mechanisms and the causes of derailments, and actually introduced a more methodical process to actually investigating derailments and what you collect on site. So as part of that, a separate group was actually formed within BR to actually specifically focus on derailment investigation. And obviously, as you can see from that previous graph, through the 1960s and 1970s, they were pretty busy people. That function became part of AEA Technology Rail when railways were privatised in the mid-90s. And then that was then taken over by Delta Rail in the early 2000s. So where do we come in, or specifically me come into this? Well, following the derailment of a train on a broken rail at Hatfield in October 2000, Railtrack wanted, or it was noted that Railtrack didn't have its own expertise and it needed some in-house expertise in vehicle dynamics. So it created its own group, principally initially to investigate rolling contact fatigue, but really to support the work of the Cross-Industry Vehicle Track Systems Interface Committee. That committee is still operating now and has a wide interest in all things to do with vehicle track interaction. But they formed a specialist group which would be able to support the work of this cross-industry committee. I actually joined that group in 2006 when I joined Network Rail, as it had become, to work on things like rolling contact fatigue. In 2010, Delta Rail said that they were going to be pulling out from track consultancy work as part of a downsizing of their business. And at that time, they still had a call-off contract with Network Rail for investigating derailments. So they were notifying Network Rail that they would be pulling out of being able to provide that sort of service because they no longer held that expertise. And various, I think, calls were put around the industry to try and solve that problem. And in 2011, the head of track asked me within the wheel rail interface team if my team and our knowledge and experience of vehicle track interaction would be able to undertake the duties to assist with derailment investigation, which I said, of course we can. So our first derailment, Edinburgh Princes Street Gardens in July 2011. I think I saw Andy Buck join the meeting, so welcome, Andy. I think, Andy, I think that's actually a picture of you there using the mini-prof at Edinburgh, but it seems a very long time ago that you and I travelled up there to see what we could do to help out the investigation of that derailment. Since the red dots indicate the different places that we've been as a team to investigate derailments. So in the last nearly 10 years now, I counted up the other day, we've actually done 43 incidents to which we've responded. So it's about one every 2.5 months. You might think that that sounds like quite an easy life, only getting called out every 2.5 months, and trouble is life's not quite as simple as that. In October 2013, we had 2 incidents in one day. How do you manage a small team trying to get to 2 different derailment sites at the same time? That's a problem. We've also had cases where we've had 4 incidents in 1 week, which again can be a bit of a headache to try and respond to. So I don't know whether it's a test for any statisticians out there, but the significance of the fact that these events very often appear to be clustered like that, I don't know whether that means anything or not, but it might do. Rather embarrassingly, we've also been to exactly the same place twice, a year apart. So been to one place, investigated the derailment, told them what they need to do, fix it, go away, come back a year later, and they've had another derailment on exactly the same twist fault. So how does the whole process work then? Well, as a team, we're based in Milton Keynes at the Network Rail Centre, and we get notifications from the National Operations Centre of just general updates of incidents that are happening around the network, which are going to have an impact on performance. So usually we'll get a text or an email alert just to say that a derailment has occurred at a particular location. Immediately then we're trying to liaise with the route and the region people on the ground. Transport is going to be significant. The event is timescales for us to get there, access, and all sort of arrangements as to whether we're going to respond or not. Sometimes we might get invited after the event, which is not ideal. So sometimes an event may occur which might appear relatively minor, and somebody say, yeah, no, it's all right, we don't need you, we don't think we're going to need your assistance, but thanks for offering. And then you'll find a couple of weeks later they may go, well, actually we started looking at this and it was a bit more complicated and we can't explain it, can you come and help us please? And by then a lot of the data or a lot of the evidence may have disappeared, so it becomes a lot more difficult to try and investigate under those sorts of circumstances. So our purpose really, so although we come from with a Network Rail badge on our coat, we're not there on behalf of rail, we are there to provide impartial investigation service. So we're there working on behalf of the industry really, and trying to keep that impartiality. And I think over the years we've had to work very hard, or we have worked hard to try and maintain that. And I think we've built up good relationships with RAIB and the train operators and the freight operating companies, and I think we have we are trusted on site to give to be part of an impartial investigation, which is good. We're there to really collect evidence to support a technical analysis to explain what actually happened. So we're not there to delve into the details of what went wrong with the maintenance processes or whatever, but we're there to give the technical mechanism of how the derailment actually occurred, and we will then assist any formal investigation which takes place with that technical input. So we're really primarily there as the immediate response to a derailment, to go and see what happened on site and then feed into the bigger formal investigation, which we will not lead. So we're not there to blame anyone. We don't lead or chair investigation panels, those for specialist investigation teams, but we will sit on the panels and provide the technical support that's needed. Generally, we don't get involved in signals passed at danger, collisions or level crossing events, because it's pretty self-evident what happened there. It's only really when we're looking at derailments on track where the mechanism may be unclear or uncertain. And the important thing is that we're not trying to compete with the Rail Accident Investigation Branch. We will work together with them on site, and again, I think we've worked hard to try and build a good relationship with them, and usually we will be sharing data with them and they'll share data with us that we've collected on site. And sometimes RAIB may well ask for our assistance on site, so they'll request that we attend and be part of the analysis and do some of maybe the surveying work on their behalf. So the investigation process, we've been alerted. What do we do? Well, the first thing is to mobilise. So actually in the centre at Milton Keynes, we've got a whole van load of measuring equipment that we can use to assist. So the surveying equipment, there's wheel and rail measuring equipment, there's a standard set of track gauges, the clipboards, measuring wheels, everything we might need on site, including the all-important bottles of refreshment, because when you go to site, you never know how long you're going to be there or what sort of facilities are going to be on site. So it's always important that you take something to look after the inner man. So then you arrive on site. And the thing about derailments is that no two derailments are ever the same. You arrive on site and invariably there's something different at every one. So in some of them, the train will still be sat over the point of derailment or around the point of derailment. It may not be such a catastrophic one, and the BRUF team will be arriving on site to re-rail, and you'll need to work around them and with them to work out what evidence or data we can collect. Other cases may be a bit more catastrophic, and our point of derailment may well be underneath the train that's on its side, and actually to be able to get the evidence from that may be a matter of days or weeks before the train is actually going to be recovered, which is, again, is a problem you need to work out, because as I said, every derailment is different, and we need to work out how to best to get the data we want at the time we need it. Other times, there may be a train nowhere near. Either the train has been removed or a derailment happened and the train traveled some distance before it was actually brought to a stand, and all that's evident is a whole load of damage to the track. So everyone is different. And so then the process of evidence collection starts. And so we've got two crucial questions that we want to answer. What happened and how did it happen? So where did the train come off and why did it come off at that particular point, and what evidence have we got to support that? Derailments very rarely have a single cause. All of them are a result as a combination of vehicle and track contributory factors. If you were to think about it, if they were to be purely because of the track, then every train should derail. And if they were purely from the vehicle, why did the vehicle derail at that particular point? So usually it's some vehicle maybe down the train which is the first to derail. So you've got to understand why that particular vehicle came off at that particular point. And so really, to think about that, we need to understand the mechanisms of derailment so we can have a better idea about what it is that we're actually looking for. So I find this chart quite useful. And really, when you're looking at derailments, you've got two main sort of processes by which a vehicle can derail. Either a wheel has to climb over the rail onto the outside of the rail into derailment, which we usually refer to as a flange climb derailment, or the rails move apart so that the wheels can actually drop inside the gauge, in which case we've got a gauge spread derailment. And what I've tried to do is classify all the different factors which can contribute to either a flange climb or a gauge spread derailment. Derailments on switches and crossings I've classified slightly differently, mainly because switches and crossings are really complicated and all sorts of things can go wrong. But most of the time when you're looking at derailments on switches and crossings, they do actually, the mechanism falls into either flange climb or gauge spread. You've just got lots of other things that happen, so it's useful to try and classify switches and crossings slightly differently. And then you've got the less frequent type, so operational issues, so vehicles overspeeding on curves and causing derailment, or what you might call total loss of wheel rail guidance, which is either because of a track fault, whether it's a broken rail or something blocking the line, or a problem with the vehicle itself. So essentially, the main mechanisms of derailment are either a flange climb or a gauge spread, or lots of issues you can get on S&C. So let's look at what happens with a flange climb derailment. So flange climb, it is what the name suggests. A wheel flange in contact with the side of the rail is able to climb up the side of the rail onto the top, run over, and then drop onto the other side into derailment. Usually when we're talking about flange climb derailment, you might hear the phrase Nadal's limit being bandied around quite a lot. And this stems from a theoretical analysis looking at the balance of the lateral and the vertical forces that are acting on a wheel. If you think about it, for a wheel to be able to climb up over the rail, it needs to have a lateral force acting on it, which is effectively pushing the wheel up. But that force also needs to overcome the vertical force, which is keeping the wheel down on the rail. So this chap Nadal came up with a limit which is based on the contact angle theta between the wheel and the rail and the coefficient of friction acting within the contact point. And he said that gives a limiting value of this ratio y over q, so the ratio of the lateral to the vertical forces. And if the actual y over q ratio acting on the wheel at that time exceeds this limit, then there is a risk because the wheel will have an opportunity to climb up over the rail. So if you think about it, it depends on the contact angle. If the contact angle is steep, then you need a very high lateral force to actually force the wheel up. If the contact angle is low, so if the contact is up here somewhere, then you need a much lower lateral force to cause the wheel to climb over. Similarly, if you've got a very high coefficient of friction, so if the curve isn't lubricated and there's no grease, or you've got contact between very rough surfaces, then it's much easier to generate the forces to climb up. If you've got good lubrication, then the force that you can generate within the contact will be limited, and all that will happen is the wheel will drop back down again. So it's very useful to consider this ratio, Nadal's limit, which is the critical y over q, whenever we're looking at derailments, and bear that in mind. How do we get a high y over q value? Well, we can get it by either increasing the y force, the lateral force, or decreasing the vertical force. So typically the lateral force increases on tight radius curves. You can also get an increased lateral force when a train negotiates a lateral alignment fault or variations of curvature within a curve, because you'll get a sudden dynamic load acting on the wheel in that direction. Alternatively, you can lower the vertical force acting on the wheel, and the easiest way to do that is with a track twist. So if you've got a track twist depicted here, when the rails, the height of the rails is moving relative to each other, what can happen is that what you need for the wheel to be able to follow it is it induces a twist in the bogie frame of the vehicle. If the suspension cannot accommodate that amount of twist, then you'll get a reduction of load on that leading wheel as it tries to dip down. Reduction of vertical load means that the lateral force can dominate and then help to cause a derailment. Slow speed, so vehicles running at cant excess can also be a higher risk of derailment, because we cant excess, the center of gravity of the vehicle and the centrifugal force is acting towards the center of the curve, so it's trying to roll the vehicle away, so it has the effect of unloading the outer wheel on the curve. Within the vehicle itself, the load in the vehicle may have an influence. If the load is offset, then it may mean that some wheels are not evenly loaded, reducing the load on some, increasing the risk of derailment. Vehicle suspension design or bogie frame twists can also help to decrease the load. So these are all the sorts of things that we look for whenever we're trying to investigate a flange climb derailment. You may notice that many derailments occur on twist faults on tight radius curves with freight vehicles at low speed, because they tick all these boxes. As I say, there's never really one factor. It's always a combination of all these things, which usually has some influence, and it's trying to work out which of these factors had the biggest influence in any derailment. You can also get a flange climb if you have complete wheel unloading. So I think most of us are probably familiar with the term cyclic top. Hopefully, certainly all the track engineers who are on the call will know that cyclic top looks like this. So it's a continuous variation in the height of the rails, all a nice even pitch, even wavelength. And what can happen in this particular case is that that vertical profile of the rail induces a dynamic response in the vehicle's suspension. And if that response is at the same, or the input is at the same frequency as the natural frequency of the bounce or the pitch of the vehicle, then the suspension will become excited, and that itself will start to bounce up and down to such an extent that the wheels can become completely unloaded, and then the wheel may just bounce onto the top of the track. As you see here, we've got a flange mark where a wheel has just bounced onto the top of the track, then run along and run off into derailment. The thing about cyclic top is, although we've got ways of managing cyclic top in track, every vehicle's response to it is different. So the response to an input of a given wavelength in the track will depend on the vehicle's speed, the vehicle's suspension. So we can see here, so this is a simulation that we've done for a vehicle running over a range of wavelengths. So from a cyclic wavelength in the track, which varies from 0 to 30 meters in length. So that's the actual wavelength of the oscillation of the top profile. And this is the vehicle's vertical response to that. So at 60 miles an hour, you can see that this vehicle actually has significant amount of unloading when it's running over a track which has a cyclic top wavelength of about 12, 13 meters in it. So that's for that vehicle, that's its particular susceptibility. You can compare plots like that for different vehicles as a function of speed. So you can see that every vehicle design, it has its own speed at which it is most susceptible to cyclic responses. As I said, that's a function of the input from the track, the design and the loading of the vehicle as well. So there's lots of factors to consider in that particular case. The other sorts of derailments you can have a gauge spread. So when the support conditions on a rail are sufficiently degraded that the track cannot sustain the gauge under the curving forces, the lateral forces imposed on it by the vehicle. As the curve radius tightens, the amount of gauge spreading forces, so the lateral forces imposed on the track, increases. And when the track components are failed and cannot withstand that, then what you get is at least one wheel dropping inside the rail. And so there's important signs to look for to indicate that. A quick look at some of the derailment mechanisms you can get on switches and crossings. Switches and crossings are really complicated. They provide a real assault course for a vehicle. Not only has the vehicle got to negotiate very sudden changes in geometry and curvature, particularly if it's taking the turnout route, but also there's changes in rail profile and track alignment as well. So it's a real combination of everything that you don't want to see on a railway in one place. But one of the things that we're looking for when looking at switches and crossings is the interaction of different wheels with the switch profiles. So for example, in this particular case, a new wheel profile as it's running into the switch is contacting on the stock of the rail and will contact on the switch further into the switch. But in this case, the worn wheel profile, so from the vehicle that actually derailed on site, its first contact with the switch is actually down near the flange tip on the top of the switch, which means that the switch could then lift that wheel up, and the wheel flange just ran along the top of the switch, and as the switch gained height, contact then passed onto the stock rail, and then it dropped off the stock rail and into derailment. So making sure that we've got the correct contact path as vehicles are negotiating switches is really important. And also the flange climb factors that I talked about earlier and the Dow's limit are important. So here we've got a switch. You can see that actually the switch has had quite a bit of batter on it, and it's got some lipping on it, which has actually worn a very shallow angle on the switch profile itself. So from the Dow's limit, we know that as the contact angle reduces, the risk of flange climbing increases, and that's what happened here. We've got a switch that isn't well lubricated, so the coefficient of friction is high, and it means that it's quite easy for a wheel, when it strikes that, then to climb up onto the top of the switch and then run off into derailment. Crossings are not immune either. Here we've got a dipped crossing, and this was a location which also had a track twist in the crossing, which meant that when the vehicle ran across it, the poor setup of the check rail as well didn't do a good job from keeping contact away from the crossing nose. So we've got contact with the wheel flange right at the crossing nose. The dipped crossing and the track twist means that actually, as you can see there, there's daylight underneath the wheel. Contact is purely on the flange, And then when the wheel gets towards the end of the check rail up here, the wheel can just climb onto the top of the rail and into derailment. So crossings are not immune from derailments as well. So that was a brief look at just some of the mechanisms. There are many more, but some of the main things that we'll try and look for. So back on site, we're there. We've got to find a derailment. What sort of challenges do we face? Well, the first challenge is the fact that as well as doing an investigation, there's a whole load of people who need to get the railway open as quickly as possible. And we need to work with them and around them. And it's not healthy to try and say, no, you can't have the railway back. I've got an investigation to do. So it's about agreeing plans of how you can work, where you can work, and working around the people who are trying to restore the track. Similar for people who are trying to recover the vehicle. So this vehicle may well have been the first to derail, and we've got some data and some evidence that we want to collect from that vehicle. But at the same time, we've got a group of people here who they may not even be working on this vehicle, they may be working on an adjacent vehicle, but we've got to agree some restrictions and what work is going to take place as to what we can do and when we can do it to be able to get the data we need from here, from this vehicle. And then of course the train may still be there, and it may be actually sat on the point of derailment. So it may actually be blocking some of the evidence that we want to get hold of. So we need to consider how we can get that, when the train is going to move. But we also need to consider that before the train is moved, what evidence or what data can we collect that will be really useful, because the train is still there and will be lost when the train is taken away. So we need to make sure that we've got all the evidence that we can collect before the train gets moved away, and we can have a closer look at the actual point of derailment. So it's quite a difficult juggling act to keep everyone happy while you're working on site and get all the data you want at the right time. So how about the investigation process itself? So we've arrived on site, we've got around some of those challenges, and now it's about evidence collection. There may be debris, damage that's all over the place, and the first thing to do is to try and separate damage which is a consequence of the derailment from that which may be causal. So we've got a site here, and we've got bits of vehicle lying all the way through the site. So the first question is, did it derail because bits started falling off the vehicle, or have bits started falling off the vehicle because it derailed? So we really need to try and understand that as the first step. Similarly, we might come to a point here. We've got the traditional clipboard marking where the point of derailment is. You always have a clipboard at point of derailment. Otherwise, it's impossible to see where it is. Things have got a habit of just disappearing when you try and take photographs of them. So it's always good to have a positive marker like a clipboard or some stones to tell you what's happening. But when we look along the track profile here, looks like we've got a dip in the track here. So have we got a track twist which is causal to the derailment? The problem is that this rail is actually hogged because damage from the derailment has actually broken all the fastenings. So we've got no way of knowing whether that rail was hogged before the derailment or whether that's happened after the derailment, when all the chairs are broken and the rail's been released from its fixings. So we're trying to weigh out that sort of evidence. And then we're looking for the point of derailment. So usually we're looking for marks, usually from wheel flanges or wheel treads on the rail, to indicate where the derailment started. As I said, when you try and take pictures of derailment marks, they just disappear from photographs. So it's always good to try and mark them with a series of small stones so you can see where they are on the head of the rail. Here, you've got a very faint line from a flange. You can see those small grooves on the head of the rail running across there. So those are actually the wheel turning grooves on the tip of the flange from the last time the wheel was reprofiled. So the wheel has made a very fine imprint in the head of the rail. Again, we've got some fine marks here marked out by the stone, so they're appearing in photographs. And this particular one, you can, because the stones mark the end there, you can actually see that line progressing all the way. It's a nice straight line across the head of the rail where a flange has actually run into derailment. And similarly here, clipboard marks the point of derailment. We've got 1, 2, at least 3 marks of derailment from 3 different wheels that have come off in the same vicinity, but this was the first one to come off. The flange marks can also tell us something really important, first indicators about what happened. And the first thing we're looking for is the length of the marks. So if you've got a very long flange mark, so in that case, it extends over about 4 or 5 sleepers, so it's pretty long, it's sort of 3 or 4 meters long. That one gives us an indication that actually it may well be something like a reduction in vertical load on the wheel, which has contributed to the derailment, because the lateral forces which are acting have not been very strong because the wheel has only slowly drifted from one side of the rail to the other. Conversely, in this case, we've got a flange mark which starts here and ends here when it drops around the outside. That's a very short mark. So what I would deduce from that was actually the lateral forces acting on the wheel are very high at that point and have been driven more by a lateral impact that's happened on the wheel to drive it over the rail, whereas in this one is more likely to be a reduction in vertical wheel load with relatively low lateral forces acting on the wheel. So there's something we can pick up just from the basic evidence. The other thing we'll look for is tread corner marks. So although here we've got the point of derailment and we've got flange marks where flange have climbed over, the wheel, the opposite wheel on each wheel set that derails then has to drop into the forefoot. And so what you'll get is a mark on the rail and on the edge of the rail where the sharp corner on the outside face of the wheel has run along the side of the rail and dropped in. So really for each flange mark on this rail, we're looking for an equivalent tread corner mark on this side, just so we can be sure how many wheel sets have actually derailed. In the case of a gauge spreading derailment, of course, you won't have any flange marks on this side, but you will have the tread corner marks where the wheels drop in. So some of them are clearer than others, but they're all there and you've got to find them. And you've got to make sure there's one for every wheel set that derailed. It's important as well to have a keen eye for detail. I don't know if you noticed the picture of me on the header slide here lying in the middle of the forefoot. Well, that was the picture I was taken. Because if you stand up and take a picture of track, you won't see features like cyclic top. You won't see the dips, they'll just disappear. So it's important to get down on the track and see everything that's going on. And an eye for detail is important as well. If you look on the rail here, you can see a varying flange mark here as a wheel has actually tried to climb up at various points and then just dropped back down as it's passed along the rail. And then, of course, it can also be useful if your train is still sat where it's derailed. In this particular case, this wheel is actually sat where the point of derailment was. This wheel set didn't derail, but the fact that it's in hard flange contact and has started to lift up because we've got daylight underneath the wheel tells us that actually there is a tendency for many wheels to want to derail at this point, and there was something different about that particular one. But it would start focusing on the fact that actually this point there is something going on to make derailment more likely. There's also more wider damage to the track that we want to look for, and it's important that you find all the bits. So here we've got a broken rail. We can look at detail at the fracture face of it. So we've got a close-up photograph of it. Obviously we can send that away and have a proper metallographic examination done. But just the nature of this fracture face can give us clues as to whether this broken rail was causal to the derailment or was it a consequence of it. So did the rail break and that's what caused the train to derail, or has the train derailed and just all the forces which are released during that derailment has resulted in that rail breaking? So it's important to find all the bits. In this particular case, the other half of this rail is sat down here. It's been carried about 4 wagons away from the actual point of derailment and buried underneath the vehicle. So we were then working with the recovery guys to try and get them to safely remove this section of rail so we could actually see what it was without disturbing this vehicle, or hopefully before that vehicle actually got removed. Sometimes you get to a difficult situation and there is very little evidence. And to me, this is some of the one of the hardest ones to actually look at. So we've got to site, we've got a train, we know it's derailed because we can see we've got wheel sets derailed. Everything has clearly kicked off around the switch and crossing area here, but a close examination of the switch has not shown any signs of flange climb marks over the stop rail, or damage to the switch toes, or impact marks to suggest that the wheel has actually split the switch. There's no real signs there, and this one was this particular one was quite a difficult one because all the signs were there was no clear mechanism by which the derailment had happened, and even examination of the detection and the locking mechanism, mechanical locking for this particular switch. There was no distress or damage to this, suggesting that the switch rail had been opened or anything. And in a case like that, where you've got no real evidence to what happened, you're starting to build up evidence from other places. And the only conclusion that we could come to in the end was that the points had actually been changed underneath the train, allowing it to run into derailment. But with no positive evidence of damage to be able to substantiate that, it's quite difficult to come to that conclusion and say that definitely is the mechanism of derailment. So beyond the point of derailment, we're also looking at damage to the track and the structures to see where the derailed wheel sets have gone. Picking up just things like flange marks in sleepers, because that tells you immediately how many wheel sets have derailed, and it's easy to follow the path of them then. So you can actually trace that back to the derailment marks, which wheel sets derailed at the point of derailment and which have been dragged into derailment because of some running of the derailed vehicle beyond that. So which are the ones you really need to focus on. And then there's the more methodical data collection. So there's track surveying that we can do to try and actually measure details of the track geometry at the location. And then also the more complicated pencil and paper stuff, detailed measurements of the track, and sketching out what we've actually seen and where it's all happened. Can also usually end up collecting some rail profiles through the site, so we can see what contribution the actual shape of the rail has had and the interaction with the wheels. So we'll want to get some general profiles, but also profiles at a more detailed resolution as we actually get to the point of derailment, because we may find that actually small changes in the profile close to the point of derailment actually had a big factor or an impact on the cause of the derailment. And then there's looking at the vehicle itself, so we can look at the wheels. So obviously we're looking for things like flange marks on the wheels where they've run over the rail to see which one's derailed first, and the general condition of the wheels. The damage on this wheel set, which it sustained from running over sleepers and ballast, is much more severe than that on the wheel set behind it, indicating that this was probably the first wheel set to derail. And then other marks on the wheel set, like scuffing marks and abrasion marks on the field side of the wheel here, indicating where it's run derailed for some time, but that's the wheel that's actually dropped into the forefoot and has been running along the side of the rail. So we've got to look for evidence all over the place. And in the same way that we take rail profiles, we're also collecting wheel profiles. That's not only just to compare them to demonstrate whether or not they were within allowable wear limits for that particular wheel profile, but they can also provide important indicators for things that may be wrong with the vehicle. So in this particular case, this was the first wheel set to derail on the leading bogie of the vehicle, and this is from the trailing bogie of the vehicle. And you may be able to ascertain that actually there's an asymmetry between the two profiles. So the profile on this side and this side have got more flange wear than the profiles on this side, whereas on this bogie, the wear between the two sides is more even. So possibly a first indicator that actually there may be something wrong with this bogie's suspension, which means that it doesn't like going around left-hand curves because it generates more wear. from, or has experienced more wear on the flange from going around left-hand curves than it has going around right-hand curves. And then that leads you to look on at more detail about the condition of the vehicles itself. So we're looking at general at the suspension. Are all the bits of the suspension there? Do they look in good service? Are we looking at any broken springs? And then further down the road, you could actually be taking vehicles apart to examine secondary suspension and the side bearers of freight vehicles to see how have they got any unusual wear patterns or broken components, or even the center bowl in this case on the secondary suspension. Has that got again an unusual wear pattern in it, or anything to suggest that there's a problem with the rotational stiffness of the bogie and its ability to negotiate curves? Vehicle loading I mentioned as an important factor in the risk of derailments for flange climb. So we can be looking at vehicle loading. We can also have a bit of a problem if a vehicle overturns and it loses its load, in which case you need to try and find other methods to actually understand what the loading of that vehicle might have been. And one way is to maybe look at other vehicles within the consist which didn't derail to get an idea about what a normal load looks like. In this case, there tends to be a general tendency for the load to become offset. So it's reasonable to assume that the vehicle that overturned also had a certain amount of offset loading. Other sources of data, so we can often end up looking at CCTV footage from vehicles. So this is a vehicle with a wheel defect approaching from the CCTV on a level crossing. But station CCTV footage can be useful for looking at the load conditions of wagons as well, to see what was in there. We can get data from our wheel impact load detector sites to maybe understand what vehicle loading conditions are. In this particular case, the first wheel set to derail was this one, which, although not significant, it did have the biggest wheel imbalance of the whole train. So it had the biggest difference of the load on the wheels from the left and the right hand side, which may be a contributory factor into why it derailed. And also we can try and get hold of the on-train data recorder to understand the speed and the way that the train was handled at the time of derailment and work back from that. That can be important information as well. So all that data then brings us into the analysis and interpretation process to understand what happened. So we'll look in detail at all the track geometry that we've collected, and we'll bring that all together. So we'll be looking at the variation of cross level through the site and then converting that into track twist. So we can see here around the point of derailment, there's quite a significant track twist. An important thing to consider is the direction of the twist. Was that twist working in combination with the curvature on the site to increase or decrease the load on the wheel set that derailed? So just to try and understand whether that was a factor or not. And then we can bring all that data together, and very often we'll end up doing some vehicle dynamics simulation. This can be really useful to help understand what happened during the derailment, the vehicle behavior, and also for doing more parametric studies to understand the contributions of different factors within the derailment. So to be able to put together a vehicle dynamics study, we need a mathematical representation of the vehicle itself. So its masses, springs, dampers, all its suspension components and where they are. And we can build a model of the vehicle. And also doing that, you can also play around to say what happened if there was a particular defect on this vehicle. So if it's maybe the friction damping components were, the friction was too high within the components, what effect would that have? We bring in the track data that we've measured, the rail profiles and the wheel profiles that we've measured, and combine those to give us the contact information. And all that feeds into a vehicle dynamics model, which we can then use to actually simulate derailment. So in this particular case, we've had a derailment that's a vehicle that's derailment on a particular curve, and we can look at the contribution of different wheel and rail profiles. So the actual wheel and rail profile combination of the vehicle that derailed, we are predicting significant wheel lift enough to derail the vehicle. But if the wheels had been different or the rails had been different, we're showing that there is actually very little derailment risk. So actually, the actual combination of that wheel and rail was significant in that particular case. Similarly, we can look at the contribution of friction. So this was at a site where there was no tight radius curve with no lubricant, very rough rail surface. And we can see that actually the state of lubrication was a significant contributor, in that the rail roughness, you needed a very high coefficient of friction to actually get derailment, but it was achievable. Whereas if the site had been lubricated, there would have been no risk of derailment. So it helps to actually inform that. So the result of all that then is that will then go into a report that we will produce, which will contain all the site evidence, a summary of all the site evidence we had, the analysis we've done, and therefore our conclusions of what we think, how the derailment happened. And that itself will then feed into a formal industry level investigation into the derailment. So that will become the technical input to that. And we'll usually end up sitting on the investigation panel as well to provide technical advice to that. So that's it really. That is the whole of our derailment process from start to finish. And what do we learn? Well, first of all, I would say no two derailments are ever the same. So you have to go in treating every day as a school day. There's always something new to be learnt. If you ever go into a derailment and go, it'll be this, the chances are you'll be completely wrong. The other thing is that you can never collect too much data. I highlighted the problems you have working with people who are trying to recover and get the railway open again. You only get one chance to collect the data because the site is being cleared up. And when it's gone, it's gone. So you have to make sure you've got absolutely everything that you can, plus more, that you'll ever need before you leave site. And most importantly, never stop asking the question why. You have to keep an open mind through all investigations. Don't jump to conclusions. Don't come up with a theory and then try to make the evidence fit. Do it the other way around. Keep asking why and think, think, think. So, thank you very much. I guess I can open the floor for questions now.
Yeah, thank you very much, Mark, for the presentation. Very detailed and very interesting. I have a number of questions already that have taken place, passed on to me on the chat. From Peter Halliwell, looking at the escalation of derailments up to the peak in 1969 of circa 400 derailments, the numbers came down very quickly the following year. What led to such a significant turnaround?
That's a really interesting question, actually. There are a number of things, and I don't think I could probably say with authority what they really were. But at the time, there were actually severe operating restrictions that were put on short wheelbase wagons to try and prevent the derailments while they were investigated. So, I mean, that obviously had a crippling effect on the freight operations at the time, but severe speed restrictions were put on the vehicles. And a lot of work was done to actually try and improve those vehicles' suspensions when they found out that there was a lot of problems with them, you know, the wheel profiles and the condition of the suspension. And it really sort of sparked the replacement of those vehicles as well, identifying that they weren't ideal. So it was a number of things, I think, that were all acting at the same time.
Mark, it's Andy Savage here. I was in the industry in 1970, and I think there was a 45-mile-an-hour speed restriction on all short wheelbase wagons at that stage.
Yes, I think you're right.
Andy, would you like to ask your two questions as you're actually on the line at the moment?
Okay, first, Mark, in case you don't know, I was Deputy Chief at RAIB for its first 5 years, and my thanks for such a splendid presentation on the overall summary of derailment investigation. I really enjoyed it. Two specific points. You say you can't have a wagon only cause derailment. I would suggest that you can. The Cheltenham wheel flat derailment in 2010, which was the day that RAIB went live, so it remains very much in my memory, was a case where a wagon had the brakes left on, and I suspect the recent Llangemach derailment on the Swansea District line had the same sort of issues.
Yes. So I think, yeah, just to qualify my statement, I wasn't saying, I was saying those sort of events are rare, and usually it's a combination.
And the second question, the two worst S&C derailments in recent years, in the last 20 years, Potters Bar and Grey Rig, and I actually wrote the Grey Rig report, both of those very much to do with stretcher bars. And I know Network Rail did a lot on stretcher bars after Grey Rig. Is that issue now fully sorted? Because again, you didn't mention it.
Yeah, I mean, there are a lot of issues that you get around S&C. And I mean, obviously from those derailments, we developed tubular stretcher bars and improved inspection and maintenance of stretcher bars. So, I mean, I can honestly say in all the derailments that I've investigated, I don't think I've come across one which has been down to the failure of a stretcher bar. So it's dangerous to say that it's fully solved, but I think we've got those issues under control.
That's very reassuring. I felt, as a permanent way engineer, quite embarrassed after Grey Rig, because we'd all been trained to go round and kick stretcher bars because they came loose, and had been doing for 20 or 30 years, and nobody had ever thought what would happen if one fully unwound under a facing point at high speed, and we found out the worst possible way at Grey Rig.
Yeah.
Thank you very much.
Thank you very much, Andy. Still on the theme of S&C, Phil Edwards has asked, do you have a feel for the comparative risk of facing point derailments between those on straight and level and those on curved, through line and canted track?
Again, that's a difficult one to answer, really, just because there are so many different combinations of geometry that you can have. Obviously S&C, which is on curved and canted track, is subject to sort of different forces and wear in different places than you maybe if you had the same design of S&C on a flat layout on straight track. But undoubtedly, I think it's always a consideration of the variations in the geometry through the S&C and the rates of change, which are important.
Yeah, it's probably a bit of an unfair question. The population of S&Cs on curved and canted track is a lot smaller than on straight and level as well. But no, I just wondered if you'd come to any sort of conclusion on that. Obviously, a lot of derailments in S&C are on the diverging path as the turnout.
Yeah, on the turnout route, yeah.
On the curved portion of it. But I was kind of quite interested in the differences between level track and canted track in terms of derailments in S&C. So that was really the question. But yeah, I appreciate, very difficult to answer. But I thought any information you had would be useful, you know.
Yeah. Okay.
The other comment from me is I don't think you mentioned it, but that big spike at in the end of the 60s and dropping off into the 70s. When I joined the railways in the mid 70s, I seem to remember that track recording was going through quite a sort of a development period, and we went into the high-speed track recording coach, and that came along. But prior to that, my impression, I wasn't around in the early 70s, but I don't think we had the track recording across the network that we enjoyed later. And I think there was a big change in detection of twists around that time, which allowed twist corrections to be dealt with quite quickly, which weren't being dealt with quickly before. I think that was my take on one of the contributing factors.
I think that's a good point. And yeah, I didn't mention that, but talking about the change in traction and the change in track construction, but yeah, there were also big changes through that time in the way that we were managing track and measuring and monitoring it as well. So that's probably an important factor as well.
Yeah.
Sorry if
All
I
right,
can come
thanks
back.
very much. Yep.
I can come back in again. We had the Neptune trolleys, which were quite good on twist, but they were quite light, and we didn't have any measure on cyclical top at all at the start of my career in 1970.
Yeah, I mean, cyclic top, it didn't really become sort of understood as a factor until then, really. So, you know, it's difficult to gauge how much of the problem we had with cyclic top before we started welding rails together. But historically, I think that the feeling is that cyclic top became an issue when we just started welding up jointed track to make it easier to maintain. But you had the ballast memory effect of the track still knew where the rail joints were, and you'd get dips generated in the track. So although we'd raised the line speed and made the geometry better, we were actually also exciting the vehicle by building these dips into it where we jointed it previously.
Okay, I have a question in relation to vehicles from Andy Batters. Many older vehicles do not have vampire models. How do you obtain data models in these circumstances?
Yeah, I mean, getting vehicle models and access to vehicle models can be a real challenge when we're doing trying to do some simulations, because the vehicle data is owned by either the manufacturer or the owner of the vehicle, and if a vampire model exists of a vehicle, that may be owned by the IPR on that may be owned by a separate organisation who actually built the vehicle model, maybe for the owner or the operator of the wagon. So trying to get hold of vehicle models can be a challenge, and involves agreement between lots of different parties about how we're going to use them. But it's strange, some of the older, very old vehicles, the data is for those vehicles, because they're sort of pre-privatization vehicles, some of the data is actually in the public domain, so you can actually get the vehicle data and the vehicle models, or generate the vehicle models. In other cases, we might use similar vehicles in a simulation and just do a comparative parametric study to look at different factors. So the whole area of trying to build up a simulation is probably one for a separate presentation, really. But yeah, actually getting hold of vehicle models and using them can be involve lots of collaboration, shall we say.
I have a question now from Steve Featherstone. Thank you for a brilliant presentation, Mark. It is one of the best PWI presentations that I have attended. If you could request 3 things of the industry to reduce future derailments, what would they be?
Oh dear. Well, okay.
Well, you might like to couple that to another one that I've had. Looking at the range of incidents in the last 10 years, this is from Andrew Starr. Looking at the range of incidents in the last 10 years, is there a ranked order of likely causes and hence a leading cause?
Okay. Well, the answer to the last one is no, not really. And what tends to happen is the minute you try and look at some data and draw out what those are, then you'll find that a whole series of other derailments happen which skew your data. And the reason I can say that with some confidence is that I've been looking at derailment data for the last few years to try and see what's changed. This year, 2020, we have had what I would consider to be an abnormally high number of derailments on gauge spread, more than we've seen in any years before. And I think, whoa, wow, where's that come? Why have we suddenly got this? But in terms of what the industry has done, actually, I think the freight industry in particular has done an awful lot. So a few years ago, the ORR actually raised with the industry concerns at the number of freight train derailments on twisted track due to offset loading. There were quite a few of them over the last 10 years. And as a result of that, a cross-industry freight derailment group was formed to try and work out what was done. And actually the industry as a whole has worked together to address that quite a lot. And I mean, if you're into railway group standards, GMRT 2141, which is about proving resistance to derailment of vehicles on, well, particularly on twisted track, that's recently been updated, and it now got some limits in it for vehicles with offset loading in them. So previously, you just tested a vehicle and showed that it got over a particular track twist and it passed. Now you have to show that that vehicle can also negotiate that track twist, but with a particular level of offset load in it. And related to that as well, we are now using our wheel impact load detector sites to actually monitor offset loads. So rather than just looking for high vertical loads to say whether vehicles have got wheel flats on them or wheel defects, we're actually looking at the difference between loads, wheel loads from side to side, to pick out wagons which may have uneven loading. So actually the industry as a whole is doing a lot to improve these things. And I really hope that that bears fruit and that I don't have to go into any more flange climb derailments because of offset loaded on twisting track. What I would say that, and it's sort of related to Steve's question, is so the first thing that's come out about the derailments that we've had on gauge spread is that actually in a lot of them it's pretty difficult to see that we've had degraded fastenings in those cases, and that we are at risk of gauge spread. So I think we need to do something to help our maintenance inspectors look for it, because many of these occur on lines where we haven't got a loaded track geometry measurement system. So it's not where our track recording car runs. So the only measurements of gauge that get done are static measurements. And obviously if you've got gauge spread, the gauge actually only widens underneath the loads from a train. So you can't measure it statically, and you're relying on somebody's knowledge and experience to look for indications. So I think I'd be quite keen on actually what could we do to actually either improve loaded track measurement or provide tools to allow track engineers to actually measure gauge dynamically without a track recording car running over it. The other thing that is a problem is just maintenance of competence, really. In the area of derailment investigation, and particularly for training our TMEs about how to maintain track and what to look for as derailment risks. So the plus side of the improvement in safety and operations and understanding we've got is that we have very few derailments now. The downside is that track engineers and investigators don't get a lot of opportunity to put into practice investigation techniques to understand what causes derailments. And that is a real challenge for us. It's a real challenge for me, trying to train new people to do my job when I pass on, because we just don't have a wide number of derailments, which is where you can get a large amount of experience from.
Well, I've then got, that's a nice lead into another question from Peter Halliwell. Is there a network of derailment investigation teams from different railway administrations? What lessons have been learned in the way investigations are carried out, and how vehicle track behaviour is modelled from other places?
So I'm not sure if Peter's question is really about from other railway administrations within the UK or around the world, really.
He doesn't. He hasn't made that clear.
Yeah,
I think he's probably talking about other administrations, not just UK.
yeah.
Unless you're talking in terms of people like Transport for London.
Yeah, I mean, RAIB have a remit to investigate everything across the whole of the UK, and they get involved in a wide range of things, whether that's, you know, not just heavy rail but light rail and heritage railways, and I'm not aware, certainly within the UK, of other operators within the UK that have a large enough structure that they've got dedicated expertise in this area. I think what we do within Network Rail is relatively unique within the UK in terms of our ability to undertake investigations at the level we do. And I think other people are very dependent on people like RAIB to get involved and do it. Other countries, obviously, they all do things different ways, but they all do have their own investigators. I've had the opportunity for a number of years now to be invited as a guest lecturer onto Cranfield University's one of their accident investigation courses. So every couple of years they run a railway accident investigation course, and usually myself and Nigel Shaw from our RAIB, we do a couple of days lecturing between us on derailment investigation. So we had the opportunity there to talk to people who have come from all over the world, who have come specifically to Cranfield to learn about accident investigation. So although we do meet investigators from other parts of the world, that's usually from a training perspective, and I'm not really aware of how they're structured within their own organisations.
Can I come in again on that, please, Kevin?
Yep.
RSSB produce regular reports as a result of RAIB's intervention on accidents on other railways, and they come out twice a month. Greg, sorry, I can't remember his name, but Greg Morse produces those.
Yes.
And they're circulated round. And there is a European-wide accident investigation branch network, or there was when I was at RAIB. Whether post-Brexit that one still exists, but certainly when I was at RAIB, we had contacts with the accident investigators in other countries and were able to talk to them if there were particular issues.
So that was governmental level as opposed to directly the administrators of those networks.
Yeah, it was an accident investigation branch or equivalent level. So, I mean, I've actually had meetings with accident investigators from Japan, from Korea, from North America, as well as from the European countries.
I've got two questions as such. Well, one question and one comment as such. Noge Leventi has asked, are there many derailments caused by track bed or drainage problems?
I think I would say there's not many, but drainage in particular can be cited in the generation of track twist in some cases, collapses of culverts or drains, and also generation of wet beds, which can then go on to generate cyclic top. I remember certainly in the case of Gloucester, that the poor drainage and the wet bed then actually started to generate cyclic top. And that's an interesting case because you've got a self-enforced dynamic behavior of the track, which actually then generates the track form. So you get a dip in the track because you've got a wet bed, so you've got a soft spot in the track. The dynamic behavior of the vehicle as it runs over that then means that actually it sort of imposes a high dynamic load further on the track, which starts to degrade the ballast and the support conditions at that point. So you then end up with two dips in the track. That then excites the behavior. So you end up with 3, 4, 5, and it just grows. So it can be an important issue in support conditions and track twist and cyclic top.
And the other question I've then got is from Matt Keller. Mark, thank you for an interesting and informative presentation. It appears that your team do an exemplary job of providing technical support to investigation derailments. Nevertheless, the number of derailments annually seems to have plateaued over recent years. Are Network Rail learning enough lessons and taking decisive actions? Do you see the number of derailments falling further, or have we reached a realistic limit?
Right, so the reason I'm laughing, for people who don't know, is that Matt actually works with me. We are in the same team. So of course, yes, absolute highest regard for the team and the work done by the team. Yeah, I mean, it's a difficult question really, because the number of derailments we've got may have may have plateaued and you think you've got something under control, but as I used with the example of gauge spread this year, something new then comes up and bites you. So you can't really take your foot off the pedal. You've got to keep your eye on everything, really. So it's difficult. It would be good for the number of derailments to fall further, but yeah, I don't really know what I can add to that, really.
I'm just looking on anything else here at the moment. No. In that case, can I ask Rebecca from the Birmingham section, as this is a joint meeting, to we don't normally have a normal sort of propose a vote of thanks, but on behalf of everybody, to thank Mark for giving such a very, very good and interesting presentation.
Yes, hi there, Kevin, and hi, Mark. Yeah, just on behalf of the Birmingham section, yeah, just extending our great thanks for such sort of in-depth and interesting presentation this month. Obviously, derailments, as you've said throughout your presentation, they are fairly low in numbers now, but I suppose this is the opportunity for us all to really refine our understanding then of what's left of root causes and what we can do to really prevent any derailment in the future. So yeah, it's a very interesting topic, and many thanks to you and your team for the work that you do.
Thank you.
And can I reinforce those comments, Mark, and thank you very much for giving a presentation which you've obviously updated quite considerably from the last time the Milton Keynes section saw it about 3 or 4 years ago.
Yeah, I think it was more than that, actually. It was a
right.
few years ago that I did it, but yeah, I like to keep the photos updated.
In that case, then, I'd like to thank everybody who's taken part in this, whether it was just as taking part as a viewer of the presentation, and those who've asked questions. Thank you very much as well to those. And we look forward to you taking part in our January meeting, which is again a joint one, when we will be looking at ERTMS and the impact of the new signalling systems on track engineers, hopefully. I'm still awaiting a summary of what the speaker will actually be presenting on. So as soon as I've got that, that will be up on the website and or distributed to the various section members. Once again, thank you very much for your participation in today's meeting. And may you have a good Christmas and New Year.